Okay, everybody, we're getting ready to do lesson 6.3, part 1 of pre-calculus math today, classwork sheet, new section here. And 6.3, part 1, you got a whopping 20 points here goes in your notebook. If you need notebook guides, email me for those. And then 44 points here on your classwork sheet, so you got a big classwork sheet too as well. So this is a big fat section here, lesson 6.3 part 1, and teachers, students, and into our bell work here for today's bell work. Solve the equations. So you have two trig equations here to solve. Give your students 5 minutes for these, teachers. I'll be back in 5 minutes for the solution. Okay, back for solutions for today's bell work. 3 secant x plus 4 equals 10. But I decided to solve this one first. So we have cosine x, cotan x minus cosine x. So to do this, you can factor out a cosine x out of both of these terms here. And you end up with cotan x minus 1 equals 0. So cosine x equals 0, or cotan x equals 1. So for either one of those, we'll solve cosine x first. So we take the cosine of 0, we get x equals pi over 2 plus n pi, or cotan x equals 1. And then when we take the cotan of 1, we get x over x. We get pi over 4 plus n pi. So these are your two solutions for this trig equation here. And then up here for this one, secant x, we can factor out a secant x equals 2 from this. How? Because we're going to subtract the 4 from 10, we get 6, and then we divide 6 by 3, we get 2. So secant x equals 2. And then cosine x, when we flip this, when we take the inverse of that, we get cosine x equals 1/2. And then in this situation here, we'll get the cosine of 1 over 2 will be pi over 3 plus 2n pi, or we'll get 5 pi over 3 plus 2n pi. So these are your two solutions here for that. And you could get this by using your graphing calculator as well, students. So there you go. Okay, into today's classwork lesson. We start out with a notebook entry. Introduction. Many quantities in geometry and physics, such as area, time, and temperature, can be represented by a single real number. Other quantities, such as force and velocity, involve both magnitude and direction. So now we introduce magnitude and direction here, and it cannot be completely characterized by a single real number. They will not give you magnitude and direction. So we start getting into physics here a little bit with force and velocity. To represent such a quantity, you can use a directed line segment as shown here. So this is the initial point and then a terminal point, and that's represented by this symbol here, PQ. And the directed line segment PQ has initial point P and terminal. Okay, going into our second page here for your notebook entry, students. Point Q, its magnitude or length is denoted by, magnitude and length here are two key words. It's denoted by this symbol here. You got 2 bars here and then 2 bars over here, actually. And then you have your half arrow up here. And it can be found by using the distance formula. So we're going to bring back the old distance formula way back from 6th grade math. Two directed line segments that have the same magnitude and direction are equivalent. For example, the directed line segments are all equivalent. So right here are examples here of line segments. They're directed with your arrows up there. The set of all directed line segments that are equivalent to a given directed line segment PQ is a vector V in the plane written as vector equals PQ with your half arrow up here. Vectors are denoted by lowercase both boldface letters such as U, V, and W. So vector V in the plane. So this is your lower plane, or lowercase in bold, boldface letters. The vectors are denoted by lowercase, and then this gives you a little bit more idea of what the vector is. PQ, line segment PQ, is a vector V in the plane written as V equals PQ, like these up here. So, okay, so this is our introduction here to really vectors, really. Very important for the rest of this course. So, example 1, equivalent directed line segments. Let U represented by the directed line segment from P00 to 3, 2, which is right here. So this is U here. We have U. Let V, which is right here, be represented by a directed line segment from 1, 2, which is here, to 4, 4, which is here. So we have two different vectors here, U and V. Show that U equals V. So how in the world are we going to do that? From the distance formula, it follows that PQ and RS have the same magnitude. So PQ, which is this one here, to solve that, we have radical 3 minus 0. So 3 minus 0 squared plus 2 minus 0 squared equals radical 13. So we have 9, and then 4 is radical 13. And then we're going to do the same thing up here with our S. We have 4 minus 1 squared plus 4 minus 2 squared equals radical 13. So that is your magnitude there. And these two bars on both sides indicate magnitude for these different line segments here. So moreover, both line segments have the same direction because they are both directed toward the upper right on lines having the same slope. So the slope of PQ, which is right here, we can find our slope here using 2 minus 0 over 3 minus 0 is 2/3. So you have a slope here of 2/3 for PQ. And slope of RS, when you figure our slope here, 4 minus 2. 4 minus 2, and then 4 minus 1 is 2/3 as well. So PQ and RS have the same magnitude and direction, and it follows that U equals V. So if two potential vectors have the same magnitude, we found their magnitude previously, and then direction by slope, it follows that U equals V. So let's try one. In exercise 11 and 12, show that U equals V. So here's our U, here's our V, and down here, here's our U, and here's our V. Okay, going into our next guided practice here. Let's see here, show that U equals V. That's for down here. U equals V. Number 12 is down here. And number 11 is right here. And 11, 12 show that U equals V. So we have U here, and then we have V here. So how are we going to show that U equals V here in this situation? This has an origin at 0, 0. And then up here we have an origin here at 2, 4. And an endpoint at 6, 5. And up here an endpoint at 4, 1. So for U here, which is here, we have 6 minus 2, and then 5 minus 4, and then we have a vector here that equals 4, 1. So that is the same as here, as our endpoint here for 4, 1 for V. So this would be 4 and this would be 1, so it would equal, U does equal V up here. And then for down here, U, I mean, both of these would equal -3, -8. Well, how do we get there? Well, U in this situation has a starting point here, -3, -4, and then it ends up here at 0, 4. So for U, so we have -3 minus 0, and then we have -4 minus 4. So we would end up with -3, -8 for our endpoint here. When we combine our values here to find our vector values here, we have -3, -8. And then down here for v, we have 0, -3, and then -5, -3. And we get the same thing. We get -3, -8. So our vector values do equal each other. In this case, u equals v. Okay, going into our next notebook page. Your page 6 goes in your notebook. Component form of a vector. The directed line segment whose initial point is the origin is often the most convenient representative of a set of equivalent directed line segments. Equivalent directed line segments. This representative of vector v is in standard position. So when you have initial point at 0, a vector whose initial point is at the origin can be uniquely represented by the coordinates of its terminal point. So the terminal point v1, v2. This is the component form of vector v. So its terminal point determines your component form of vector v. Written as v equals v1, v2, just like here. The coordinates v1, v2 are the components of v. So the components comprise of the terminal point. If both the initial point and the terminal point lie at the origin, then v is a 0 vector and is denoted by 0 equals 0, 0. Okay. So, notebook page 7, component form of a vector. The component form of the vector with initial point p, p1, p2, and terminal point q, q1, q2, is given by vector pq equals q1 minus p1. So this is your initial point, this is your terminal. So terminal minus initial, then terminal minus initial, equals v1, v2, which equals your vector. So this is your vector value here, determined by the difference of your initial point and your terminal point. The magnitude or length of v is given by, the magnitude or length is given by, the magnitude here is denoted by these two symbols here. The radical q1 minus p1 squared plus q2 minus p2 squared, which will equal v2, v squared 1, or rather v1 squared plus v2 squared, radical of the sum of these two values. So if the magnitude v equals 1, then v is a unit vector. Moreover, the magnitude v equals 0 if and only if v is a 0 vector, 0. Another notebook entry here. Two vectors u, which equals u1, u2, and v equals v1, v2 are equal if and only if u1 equals v1 and u2 equals v2. For instance, in example 1, the vector u from p0, 0 to q3, 2 is u equals vector pq, which equals 3 minus 0, 2 minus 0, which has this terminal point here of 3, 2 of your vector. And the vector v from r1, 2 to s4, 4 is v equals vector rs would equal 4 minus 1, 4 minus 2. It also has a vector value here of 3, 2. So going off into our next example here. Example 2, finding the component form of a vector. So find the component form and magnitude of the vector v that has initial point 4 and -7. So we need to find component form and magnitude of the vector v and the terminal point of -1, 5. So here's our initial, then here's our terminal. So let p equal 4, -7. 4, -7. This is our initial, denoted by p1, p2, and q equals -1, 5, which is q1, q2. So as shown here, here would be a drawing of this vector here. So here's our initial here at 4, -7, and then our terminal up here is -1, 5. So that would be a diagram of it. So find component form and magnitude of this vector here. So to do that, here again is our diagram. The components of V are V1, V2, which are V1 is Q1 minus P1, which equals -1, -1 minus 4, so which equals -5. And then V2 would be Q2 minus P2 would be 5 minus the -7, which equals 12. So our magnitude here will be determined by radical -5 squared plus 12 squared, which would, in these values are taken up here, V1, V2, and here. We square them underneath the radical, and then we come up with radical 169, which equals 13. So there is our magnitude here of this vector here. So let's try one. In exercise 13 through 24, we got 15 and 16. Find the component form and the magnitude of the vector V. So here's our vector here for 15. 16, here is your diagram of that vector as well. So up here for 15, and the initial point is 2, 2. Our terminal point is -1, 4. So to find our V, we have -1 minus 2, -1 minus 2, and then 4 minus 2, which will give us -3 and 2. This is our vector value here. And then to find our magnitude, we stick these underneath the radical, square both, add them, and then take the square root of 13. And there is our magnitude for this vector here. So the component form is here, and then here is our magnitude, which the magnitude of V would be 3.61. And then down here, same thing, our initial point is down here. I'm going to let you do these, students. I mean, I set this up for you. Go ahead and continue that, okay? Into our next notebook slide here. Vector operations. Two basic vector operations are scalar multiplication and vector addition. Geometrically, the product of a vector V and a scalar K is a vector that is K times as long as V. So K times. So we have a vector V and a scalar K. Is the vector that is K times, the absolute value K times as long as V. If K is positive, then KV has the same direction as V. And if K is negative, then KV has the opposite direction of V as shown. So we have V here. This is 1/2 V. This is 2V. And then negative V would be going back the other way. And then -3/2V would be going back the other way, but 1/2 as long as V. Classwork, page 14. To add vectors U and V geometrically, first position them without changing their lengths or directions, so that the initial point of vector V coincides with the terminal point of the first vector U. So, for example, the sum of U plus V is the vector formed by joining the initial point of the first vector U with the terminal point here, of the second vector V as shown. So you just continue here with U. U would determine the direction here, the slope, say, plus V, and then V would be the end point of V, and then you just tack that on to U and extend it out like that. Notebook entry. This technique is called the parallelogram law for vector addition, because a vector U plus V is often called the resultant of vector addition. And it is the diagonal of a parallelogram having U and V as its adjacent sides. So This would be an example here of the parallelogram law for vector addition. We have u plus v, then we have u here, then we have v here, and then where v ends up, u plus v, this is where the endpoint would be there. So you'd have a parallelogram kind of situation. Definition of vector addition and scalar multiplication. So let u equal u1, u2, and v equal v1, v2. Be vectors and let k be a scalar, a real number. So then the sum of u and v is the vector u plus v equals u1 plus v1, comma u2 plus v2. So this is your sum. The sum of u and v is the vector like this. And the scalar multiple of k times u is the vector ku. Ku equals k times u1, u2 equals ku1, ku2, scalar multiple. Classwork. The negative of v is v1, v2 is, the negative v would equal the negative 1v equals negative v1, negative v2. So that would be the negative of v. And the difference of u and v is u minus v would be u plus the negative v. So this would be add to negative v to this. So you have u here. And then this would be u minus v here would be this length. Then here's your v here, negative v. Then u plus a negative v would be here. And then here would be your positive v. So u1 minus v1, and then u2 minus v2 will be your difference. To represent u minus v geometrically, you can use the directed line segments here. So here's a geometrical representation of the addition of negative v. With the same initial point. The difference, u minus v, is the vector from the terminal point of v. So the terminal point of v, u minus v, so terminal point of v, u plus a negative v, to the terminal point of u, which is equal to u plus a negative v. So u plus a negative v would be out here. Okay, into our next example. Example 3, vector operations. Let v equal negative 2, 5, and w equal 3, 4, and find each of the following vectors. A would be 2v. So, because v equals negative 2, 5, you have 2v would be 2 times negative 2 and 5. And then that would equal 2 times negative 2, 2 times 5. That would be negative 4, 10. A sketch of 2v is shown. So here is our initial here would be v, would be negative 2 and 5, be our endpoint, their terminal. And then when you multiply it out, it goes out here to negative 4, 10. So that would be 2v. Okay, so w minus v. So the difference of w and v is w minus v equals 3, 4 minus the negative 2 and 5. So w minus v would equal 3 minus negative 2, and then 4 minus 5. And this would become 5 negative 1, be the difference of w minus v. So the sketch of w minus v would be shown here. So we have here w minus v will be 5 negative 1 would be here. So w is 3, 4, and then v would be negative 2 and then 5. So minus v. So in this situation here, we were subtracting negative 2, 5 from w here, and then we end up down here. So this would be the difference of W and V, would be 5, -1 down here. Note that the figure shows the vector difference W minus V as a sum plus W plus a negative V. So W plus a negative V would be, again, 5 and -1. Okay, more classwork here. The sum of V and 2W. So V plus 2W, so a -2, 5 plus 2 times 3, 4. So -2, 5 plus 2 times 3 and then 2 times 4 would be -2, 5 plus 6, 8. And then -2 plus 6 and 5 plus 8. That'll give us 4, 13. So a sketch of V plus 2W is shown here. So V would be -2, 5, which would be over here. And then 2 times 3, 4. So 3, 4 would be 6, 8. So 6, 8 would be out here somewhere. But when we add them together, we end up with 4, 13 by using our analytical way of doing it. So we end up with a terminal point here of 4, 13 for V plus 2W would be 4 and 13. Okay, starting in here for our guided practice, page 22 of our homework. 37 through 42, find A, which is U plus V. B is U minus V in this situation. And then C is 2U minus 3V. And then D will be V plus 4U. So, our first situation here is U plus V, which is 11 plus 3. Here's our U. Then here's our V. When we add these together, we get 11 plus 3, which would be out here. And then here's your geometric solution for that as well. U and then V. And then we add here U plus V out here. And we get out here 11 and then 3. And then B is U minus V. Would be -3, 1. So U minus V would be -3 minus plus 1, actually, plus 1. And then graphically, this would be your solution here, would be out here. And then 2U minus 3V. So 2U minus 3B be 8, 4 minus 21, 3. So 2U minus 3V would be 21 minus 3. That would equal -13, 1 for that one. Here's U minus V back here. U minus V would be -3, 1. So a -13, and then 1 would be right here. -13, 1 on this grid here. This will be your -13 minus 1. This is 2U, and then this is -3V here. And then you come back together here for your solution at -13, and then 1. And then D here, V plus 4U. Let's see, that would be V, which is 7, 1, and then 4U. Here would be 16 and 8. We add those together. We have 23, 9. Here would be your 23, 9 up here. Then here's your geometric solution here for these. Okay, so that would be your solutions for number 37. And this is, and that's your lesson 6.3 part 1 classwork for pre-calculus math today. Email me here if you need solution PowerPoints, homework sheets, classwork sheets, any other course materials. This is my email. Thank you.